we now have a formula, or even two. They're the same, but we can write them with different notations, this being a little bit more compact, but this being directly what we derived. And we need to see a concrete example to see how to use them. So let's use some physics one-on-one magic, get rid of most things, and then go into the example that you can find on lecture notes. Okay, so we have space in the board, and the example that you can find on section 4.4. And in section 4.4, what we want to differentiate is function f of x being x squared. We're starting simple and easy. Now, how do you actually use this? It's relatively straightforward, provided you understand what these terms mean. What you want is to calculate these independently before you sub them in. Maybe you have a lot of practice and you can do it directly. If not, I would suggest that you start with steps. So this term you already know, that's x squared. This is what you're going to plug in here. This term you kind of need to calculate, and you want to calculate f of x plus dx. So what you do is give this as an argument to the function and then retrieve it. So in this case, if you give x, you get x squared. So if you give x plus dx, you get x plus dx squared. And you can expand on this, so this gives you x squared plus d squared plus 2 times x dx. So you have the basic ingredients to calculate the limit. So I would say that this is step 1. Step 2 is you're going to plug in into the formula. So let's get rid of this. And we want to calculate f of x, which is the limit when dx goes to 0 of x plus dx minus f of x over dx. And we can now sub in, so this term is actually equal, so don't forget to keep the limit until you sub things in, as x squared plus dx squared plus 2x dx, and then you're subtracting f of x, which is x squared, and you're dividing by dx. Right, so this is the basic principle. You obtain the terms, you plug them in, and now it's really just about solving the limit. So it means that the next step, and I'm going to get rid of this so we have some space. You can cancel out x, and it means that when you look at the limits, so this is something relatively straightforward to obtain. We're starting easy. You can actually cancel out the x, and this is of course because the x never really equals 0. It tends to 0, but it's never really equal. So this results in the limit when dx goes to 0 of the leftover terms. So there's a dx here, and there's 2x. So this is one of the straightforward limits where you go to number 1 of ways to solving limits, which is you can actually sub in. This is 0 plus 2x, which is equal to 2x. So it's not surprising that the derivative of x squared, remember this was the function we were looking at, is 2x. You should be familiar with that differentiation rule. But you can actually prove it very, very simply from first principles, just calculating this limit. And for most of the cases, it's just about plugging in the functions in the formula and trying to get rid really of the x, because the limit goes to 0 and you don't want it to be a problem.